Good afternoon, everyone. I really appreciate you joining us today. Please, you can continue to introduce yourself in the question area. I have to tell you that I can't find the question area, so Eric's going to be passing along your thoughts to me through the webinar. As a heads up, make sure you have a pencil and some paper available, because we're going to be looking at a few math problems, and I'll also be asking you to draw a sketch later on in the webinar, but don't be afraid of that if you're not an artist, because I'm not either, but it's just a simple sketch. And I'm also going to try something a little different in regards to the question area. So in order to give everyone equal time, I'll be asking you to put in your responses when I ask you to think about something. But you don't necessarily have to hit enter just yet, so everybody has equal think time. Now, before we get started, we have a quick poll. And the poll is, how comfortable are you in teaching algebra to your students? So Eric, can you start the poll, please?
Yep, it's open for folks. And 30%, 36%. Lots of people voting.
Thank you. Again, how comfortable are you in teaching algebra to your students?
Okay, we're just at about 80% of voting. You guys are on top of this. We've done polling at some of the other webinars, and you guys are voting quickly. You know what you think. I'll give it just a couple more seconds, and then I'll close the poll. We're at 85%, so that's a pretty good selection. Okay, so the number one is I'm very comfortable teaching algebra at 41%. Number two is I'm a little shaky, but I can get by at 35%. My students are low level or ESL at 15%, and I have math fears of my own, so teaching is scary.
Okay, great. Those are great poll results, and you know why? They're very interesting to me because it really applies to our webinar today. We know that with our students, they have different comfort levels when it comes to algebra as well, don't they? So today we're going to be looking at how we can help our students who are at various places in their math journey, just like we are. And let's start by looking at a particular problem that was used by researchers to get a sense of how students approach problem solving. So here it comes. I think, if I can forward it. There we go. All right, so what number goes in the box here? Now you probably have something in your head right now, but what would your students say? So if you want to go ahead and put a response in the question area, we're interested in what your students might say should go in the box. We're imagining how they might respond. So go ahead and put your response in the chat box, please.
So,
in the question.
So a variety of responses. So some say that their students would say 7. Some say that their students would say, I don't know, or that they would give up. And some say that their students would say 12.
Okay, so I'm curious, for the folks who answered 12, why do you think that your students would say 12?
Some people because of the equal sign.
Okay.
Right. They would try to solve the first part of the problem, and they read from left to right, and they're really used to seeing the equal sign meaning answer.
Right.
And they don't really understand what that equal sign means necessarily.
All right. And so for the folks who thinks that their students would answer 7, it's because the students are seeing that the equal sign expresses a relationship between these two expressions that are on each side of the equal sign. So here's some background on this particular problem. It was the basis of research that was conducted with elementary students, middle school students, and adult ed students. So let's look at the results from the adult ed students. So this problem that we were just thinking about was given to students who were sitting around waiting to be interviewed. Pam Meter conducted this practitioner research. And when she asked these students, these were all new students. They had just come in for placement tests. They hadn't been placed in classes yet. And she was really curious as to how students' ability to answer this question correlated with the level class that they were eventually placed in. Now, in her program, level A was the lowest level math class. So I'm curious what you are noticing about her findings. So what do you think is interesting about what you see in the data that she collected? And if you could go ahead and respond in the question area.
Right. As people were still responding, some people had said that they thought their students might say 17, right? That they would add everything up. So Nadia suggests that the lowest level will solve the problem as an addition problem. Caitlin notes that it's interesting that the answer 17 becomes more likely in the higher level classes, except for the highest. And then sort of the higher level, the more correct. Just sort of generally understood that many people are confused by the equal sign.
Mm-hmm. Yeah, so I was wondering if anyone would think that their students would answer 17 because they're just seeing operation signs there. They're seeing addition, they're seeing equal, so they just add everything and then think that that's the answer to the equation. So the interesting thing I found about this data is and actually Pam's conclusion after doing this research was that students at all levels seem to struggle to answer the question. It did seem like higher level students, the students who were placed in the higher level classes, were better able to answer the question. And I have to tell you that personally, I have presented this equation to a number of different classes over the last several years, and I have seen that students often choose 12 as the answer. Some students get it right. A few students pick 17, but even seasoned students pick 12. So really the main takeaway from these results is that our adult ed students very often don't have correct understanding of the equal sign. They have an operational view of the equal sign instead of a relational view. So what exactly does that mean? So take a few minutes to notice how these middle school students answered the question. What does the equal sign mean? Now, the researchers identified 2 different mindsets that students had. They either view the equal sign as something that signals an operation, like the problem we looked at, 8 plus 4 equals something, and it really doesn't matter what's on the other side, and the answer is, or they understood that the equal sign means exactly that both sides of the equal sign have the same value. And what I really found interesting about this particular study done with middle school students is first they gave them this question, what do you think the equal sign means? Then they gave these students some problems where they had to solve for X. And what they found was a direct correlation between the understanding that students had of the equal sign and their ability to make sense of the problems and solve them correctly. And the students who had a relational thinking were able to answer more questions correctly. And this actually was true regardless of whether or not they had any formal algebra training. So it's interesting to me because developing understanding of the meaning of the equal sign has typically been thought of as a basic math concept that students learn early on in elementary school. Yet research is showing us that students at all levels often are limited in their ability to solve math problems because they think of the equal sign as signaling an operation rather than as a signal to look for balance. That particular study also showed that students need repeated practice in order to change their mindset from operational thinking into relational thinking. So often we have a limited amount of time with our students, right? We can only do so much, but what can we do to reinforce a relational understanding of the equal sign? So I'm going to share some activities today that support a relational understanding of equality. This idea that's based on balance, which in turn is going to help our students to bridge to higher level mathematics because they're approaching math with the goal of sense-making mindset. I'd like to mention that most of the activities that we will be working through today are found in this resource that's going to be available to you at the end of the webinar. This resource was developed to address questions most often missed on high school equivalency exams. It can be used for independent study, or it can be used with students in our classes, which right now are virtual classrooms, but you can just screen share with them and use it that way. So the number of the day is the first routine that we're going to look at. It's an instructional routine that, as the activity suggests, can be a warm-up every day in class. It's student-directed. It works very well to level the playing field with a group of mixed ability students. So the idea here is to make a statement that equals the number of the day, whatever number you decide to pick, or draw a picture, or create an expression that equals the number of the day. So now what I'd like to do is take a look at some of the responses that I got from students when I gave them 9 as the number of the day. Now this was a Zoom class that I had, and you see what students' responses were. I'd like you to comment on what you notice about these student responses. What do you notice about how the students responded to number of the day? What equations did they create? So if you could please put your responses in the question box.
So Dora suggests that they're all operational.
Okay.
Rebecca says that there's a huge variety and it's nice. Casey says sort of basic math problems. Maggie notes that a few students use multiple equal signs in the same expression.
Okay.
And Caitlin says she's impressed with the student who utilized the order of operations. Jane says she thinks that they're sophisticated. There's an exponent, division and addition operations. There's some creativeness, and there's the different. Alex notes that there's seemingly different learning levels represented.
All right, so that's one of the goals of number of the day, is that there are anybody at any level can participate. And as you brought out, there are many different kinds of problems that we see here. So then, could all students participate? Yes. What do you notice about students' understanding of equality? Do we Do we think students are all understanding what the equal sign means here? And you could go ahead and put a response in
So
the,
yes, no. So
hmm,
as Denise points out, 9 does not equal 3, so no.
all right. So I'd
Not
like to
all,
tell you,
yes.
okay, I'd like to tell
Okay.
you a little, go ahead.
Nope.
Anything
Yeah.
else?
Nope. So yeah, everybody's saying mostly except this one here on the bottom.
Right. Okay, so mostly everybody seemed to understand the equal sign. I'd like to tell you a little story here about one of the students. So this here, 3 squared equals 9, was her first response. The students wrote this themselves on the whiteboard. And I thought, oh wow, this is great. She actually understands exponents. So I decided to push the students because she put that, the one right above it, 3 plus 3 plus 3. I thought, I think I know this student can do something a little more complicated than that. So I said, all right, everybody, I would like you to make it an equation, but have 2 operations. So the student who just put 3 squared then put this instead, what you see on the bottom. And it shows really that she was thinking deeply about that 9, because both of her expressions, 9 divided by 3, 6 take away 3, you can see where the 9 is there. But do they equal 9? No. So this really, I thought, was important because it showed me that just because she could do a problem with an exponent doesn't really mean that she understood what equality is or what the equal sign meant or what it was signaling. So we did have a conversation about that. And then she wrote this. This was her 3rd attempt at the number of the day. So one more thing you can do with these student-generated expressions to get them thinking about equality and balance, and it's great because you're using expressions that students already created, is to take 2 of them and put them on opposite sides of the equal sign, and then ask students, is this true or false? And then follow this up by asking students how they know it's true or false. The true-false statements are very valuable in uncovering student thinking because it requires more than coming up with just an answer. Students really need to evaluate the expressions and the equations as true or false, so they have to consider both possibilities. I really like using true and false to help our students to build a relational view of equality. So let's look at how we can build on that some more. So as you're looking at this, you might think that these problems are really too simple for your students, but I'd like you to take a look at them thinking about what properties or laws of mathematics might come to your mind. Please select one or more of the equations that you see listed. Say whether you think it's true or false, and then maybe explain why you think it's true or false. So go ahead and put what you're thinking about them in the question area. You could choose one or more.
So Mary's saying that number 6 is a really excellent idea for her students. Mary, do you want to say why in particular? Okay, Takesha's noting that number 6 is false. Mary suggests that number 6 would be particularly helpful because of the confusion of the value of the exponent. Michael is saying number 2, a plus b equals b plus a. Stephanie also likes number 6 because she feels like it's tricky and it could be used on an exam. Caitlin points out that the 2.5 equals 7 plus 1 is false, but a student would say it's true for the same reason in the first problem, right? That they see the equation and they think it's the solving for Number number 2 is true. Number 3 is a great example. Sherry says, and that she would ask them to prove it visually.
Nice. Yeah. That's a
Nadia
great
says she would
idea.
use all of them as a warm-up or a class discussion. Danielle suggests that most of them still do that with number 6, no matter how good they are at math. When they're rushing, they're going to make that kind of mistake commonly. Mary
Mm-hmm.
also points out that she feels for her students, right? I think we all do, I would hope.
Right. Right. Um, so you've mentioned, I heard a few the algebraic laws or properties or mathematic properties that we actually see exemplified in these equations. I think I heard A plus B equals B plus A. Although I think it's important to say that these laws of mathematics are true no matter what level of math that you're teaching. They don't need to be named so abstractly or formally as you see on the screen. I mean, these are things that are just true about math and how it works, and they don't change. Students at all levels can benefit by articulating these laws in their own words. Now, to extend this activity, you might take one of these false statements. We focused a lot on 6, but let's look at the false statement in number 1. And you might ask your students, what could we do to make this statement true? So what do you think your students would say to try to make this statement true? If you could put your response in the question area.
Add a 1, get rid of the 1.
Mm-hmm. Yep.
Takesha says that she thinks that they would change the numbers and not the signs.
Ah.
Elvin suggests similar, that it would become 7 plus 0.
Mm-hmm.
Renee suggests that they might change the multiplication for 7 times 1. Yeah, mostly changing the numbers.
All right. Thank
Or
you.
Michael also points out that they might put a not equal sign.
Ah. Okay. All right. So there's lots of things, and I like this because there's a big variety in what our students could do with this. One bridge that we could use, well, we could use this as a bridge to change the sign, like someone suggested, but what about an inequality sign? This is a great way to get our students to be able to make a true statement out of this and bridge to inequalities. So another thing we're going to look at today is visual models. That's the next thing. Visual models are really something that can help our students to gain a better understanding of equality in a way that's going to help them to understand the rule. What you do to one side of the equation, you have to do to the other side of the equation. And I just want to tell a little story about a student I had. I think we probably all had students who've come into our classes with rules in their head that they kind of misremembered, and they try to carry them into adult education, but they have them a little mixed up. And I had one student who kind of sort of remembered the procedure that you see on the screen. And sometimes she was capable of working through it to solve a simple problem where you had to solve for x. But then when I presented to her with the problem we looked at earlier, she chose 12 for the answer. And I really wasn't surprised about this because I had seen her struggle to solve problems when she did not have a procedure to fall back on. She was not used to making sense of problems. So if we start with visual models to try to help our students to bridge to higher level algebra, that's going to help them to develop sense making and this relational view of the equal sign. So let's look at a visual model. I'd like you to comment on what you notice about this visual model in the question area. What are your thoughts about this?
As people are kind of thinking, and I'm responding to that, there's a question from Elvin about whether or not you think all students do learn from visual models.
Well, that's a really good question. I know for myself, I'm just thinking of myself as a student. I did not learn through visual models. I learned procedures. And then when I started doing professional development classes, not when I started taking classes, I had to learn how to use visual models to model the math that I already knew the procedure for, but the visual models helped to deepen my understanding of the procedures that I already knew, or I had like these aha moments where, oh wow, that's what the procedure meant all this time. I didn't even know that. I could do the math, but I didn't know the procedure. And research does show that using visual models really improves student performance.
I think before I pass along what some of the folks are saying, I think this often comes up when people talk about what type of a learner a student is. You know, and they'll say, oh, somebody's a visual learner, somebody's a kinesthetic learner, somebody's kind of like a verbal learner. And I think that that's always really problematic, right? Because we all learn in a multiple of ways, right? And it's a question of what we prefer when we're trying to learn something, right? So if I'm cooking, I would rather read a recipe than watch someone on a video, right? But that's not everybody. If I was doing something else, I might want to see somebody perform that. So I think the same can be said, you know, within the using the visuals, right? That there are going to be some problems for some students where a visual will be helpful, and maybe for some that it's not, right? So it's not a one size fits all for every kind of problem. Um, so
Right, and to add to that,
Yep.
there are sometimes adult students are put off by visual models because they feel like it's something that's only used in elementary school. So uh, I'm usually able to get my students over that hump, and they end up enjoying it though. But yes, you're right about. Thank you for those comments.
Yeah. So people are sort of to your point about understanding visuals, people are saying that it's balanced, and some people are also saying that it's not balanced.
The visual model
Yes.
that's up here now?
Yes.
Okay, so could I have some comments on why you think it's balanced or why you think it's not balanced?
Some people are saying that there's more on the right. Some people are saying that the W equals 3, and so therefore it's balanced.
Okay, all right, so let's take a look at this visual model and break it apart and see what we can figure out. So imagine that this is a hanger diagram, first of all. So it's like a hanger, but we're just not seeing the hook on the top. And imagine that we're hanging weights on both sides of the hanger. If the hanger is balanced, then the left side of the hanger is not going to be hanging down, or the left side, the right side isn't going to be hanging down. They're going to be straight because it's balanced. So someone else noticed that the W might be a different weight than the 1. So in order to keep it balanced, let's think about the rule that is commonly used in algebra to solve for x. What you do to one side of the equation, you have to do to the other side of the equation. So let's look at how this would play out visually with a hanger diagram. So in what you do to one side of the equation, you have to do to the other side. If we do that with this visual model, we see that there's 5 W's on one side and 3 on the other. So if we subtract those 3 from both sides of the hanger diagram, let's just imagine that they're gone now, and we still have a balance because both sides are, it's not toppling, and they're equal. And what else could we do? What else could we take away from both sides and have it still be balanced?
The
Does anybody
ones.
want to?
Yes, everybody's saying the ones.
Okay. So we could take these 2 ones away from both sides. And let's just imagine that they're not in the picture anymore. And what do you have left? You can't really take anything else away because the W's are not the same weight as the ones. And so someone had mentioned that W was 3. They figured that out because you have 2 W's there and 6 ones. And did anybody come up with an equation that would have represented this?
Not with the variables, no.
All right, so let's take a look at what that would look like. So this is what your students would be presented with, and they would be asked to solve for X by what you do on one side to the equation you do on the other side. But we can use the hanger diagram to help us to actually do that, and we're gonna look at that a little bit more.
Before you move on, Roger suggested that sometimes the letter variables make it confusing for his students, and so he replaces them with a smiley face, and they seem to get a better understanding, right? That there's you can modify these in ways that help students really get to the point.
Yes, yes, and that actually leads right into what we're showing on the screen right now, which is 2 different hanger diagrams. You might introduce your students to hanger diagrams with this rather than with something that is more complicated like we just looked at a minute ago. And earlier this week, I sat in on Eric Appleton's Zoom class, and these are some of the comments that his students made in response to what do you notice. So they noticed that it was balanced. They said they knew it was balanced because the line is straight. And they concluded that the 2 squares were the same weight as the 1 circle. And here they notice it's not balanced, and they thought that the circle was heavier than the square. So this is a screenshot of his class, and it's worth noting because as the students continued to look at the diagrams, they were able to articulate that 1 box plus 1 box is equal to 1 circle, similar to the observation with the smiley faces. So this is kind of an early introduction to the use of variables with shapes standing in. Moving along in Eric's class, these are the questions that his students were thinking about. So at this point, his students were understanding the idea of balance, that there's a relationship between the 2 sides. They were understanding that the hanger diagram on the left was not equal to the right. And they're understanding that shapes are representing an unknown value. And they developed some good questions to push the conversation forward. Now, this is an actual class that just happened in a virtual environment in a Zoom class. So then they moved to imagining that the value of the square was 4. And this new information that was given to the students helped them to then be able to figure out the value of the rest of the shapes that had no number in them. It helped them to develop this relational view of equality, and it helped them to see visually how the hanger diagram is balanced or unbalanced in terms of weight. So now I'd like to just spiral back for a minute to the true-false statements as they could be used with hanger diagrams. So you see something on the screen here. Do you think this is true or false? And explain how you know. Please put that in the question area.
So false, but Eric points out that many of his students would say true. Somebody says true. The balance hanger is true. False because 4/6 reduces to 2/3. False because they didn't add the fractions correctly. So mostly false, couple trues.
All right, so here is a way for using this hanger diagram with true-false statements. And I chose this specifically. I mean, you could put any values in a true-false statement, but I chose this specifically as a distractor because I knew that my students sometimes are going to very commonly add 2/3 and 2/3 and make it 4/6, when in fact 2 and 2/3 plus 2 and 2/3 is 5 and 1/3. So the statement is false. But true-false statements, like I said before, give our students a different level of thinking. And using the hanger diagrams is a great way to bring this into our classes. So once our students have had plenty of practice substituting numbers for the shapes, we can introduce a hanger diagram with variables. There's are different ways we can approach drawing out student understanding with this. One way would be here to solve, asking your students to solve for W. When Eric had his class, this is what his students noticed. They were noticing things and he was annotating what they were saying. So what understanding do you think Eric's students were getting out of this? If you could respond in the question area.
While people are typing up, Sherry wanted to point out that she likes that you present the simple challenge of asking true or false and having the students find their way through the calculation themselves. Okay, so, all right, so what's W? That the left must equal the right to stay balanced. Sort of how to make an algebraic equation of any problem. Right, these are things that people are thinking.
All right, so one thing that I really appreciated in sitting in his class is that when one of the students said, well, on the left side of the diagram, it's 2 plus W, and another student piped up, yeah, but it's also W plus 2. So there again, here was a way where they were using one of those laws of mathematics, and students were recognizing they were able to solve for W using the hanger diagram. But remember, one of our goals is to have our students be able to see that rule. So with this particular hanger diagram, if you take away from one side the same as you take away from the other side, it becomes very clear then that W is equal to 3.
And Sherry points out that that this visual model really helps emphasize that the equal sign at the top of that hanger chart is the equal sign, right? That it's representing that balance.
Thank you, Sherry. All right, so here's that same hanger diagram, and we can approach it a different way. instead of asking students to solve for W, we could give students multiple choice questions where they have to choose which equation matches the Hanger diagram and explain why they know that their choice is correct. So the reason why we might want to try using this at times is because it does require a different way of approaching the problem, a different way of making sense. Some students might even find this helpful in terms of being able to relate the Hanger diagram to an equation. I heard that response in Eric's class the other night. Also, there are equations here. We know that B is the correct equation because we have already looked at this in the past slide. But having these false statements also that are distractors, that represent errors that students really are likely to make, helps us to be able to have these conversations with our students. Like, okay, if A is false, why is it false? And we have students explain their thinking so that they won't, that we find out whether or not they're really understanding that W plus 2 equals 5. Also, multiple choice is what students are going to see on tests. So it's really good test practice. So another way to approach Hanger diagrams is to ask our students to write an equation that matches the Hanger diagram. So please look at the Hanger diagram and write an equation that would represent what you see in the Hanger diagram. If you could put that in the question area, and just saying that there's more than one way to write an equation for this, that your students will come up with different ways.
All right, so 4x plus 8 equals 2x plus 26. 4x equals 8 equals 2x plus 26. 4x plus 8 equals 2x plus 26. That's the x plus x plus x plus x plus 8 equals x plus 26. Oh, there's a typo in there, one of them, yeah. 2x plus 8 equals 26. Yep.
All
So
right.
mostly variations of that, yeah.
Thank you. I didn't hear anybody put the answer in because we weren't asking our students to do that, but they probably will anyway. But one thing I really like about this is that you can use this as an opportunity to even bridge to things like combining like terms. And as I said, you're not asking students to solve anything. You're asking them to recognize what the equation would be. I just want to point out again that everything we've seen so far is coming from that Tools of Algebra packet that will be available to you at the end of the webinar. So I want to move into the main activity for the day, which is a Hanger diagram challenge. If students understand how Hanger diagrams work, they can use them as a tool when they're tasked with solving for X, even if they don't know the formal rule of what you do to one side of the equation, you have to do to the other side. They could draw a Hanger diagram to help them to solve the equation. In fact, actually, it's advisable to introduce students to visual models that represent balance before they're introduced to formal rules. So now let's try that together. This is why I asked you to get out your pencils and paper. So you see the equation that's on the screen right now. Let's work together to draw a Hanger diagram that would represent this equation. And since we can't share our sketches in the chat box, I'm going to ask that when you finish with your diagram, if you could take a photo and then post your image to Twitter using @Patricia Helmuth. or the hashtag ANN math. Give you a few minutes to do that before I check the Twitter feed. In the meantime, I'd like to mention I'm going to be writing an article that's going to appear in the next issue of The Math Practitioner, which is the newsletter that is published by the Adult Numeracy Network. And it would be great to have a few photos of your hanger diagrams that you come up with today to include in the article. And I also wouldn't mind at all if I had some examples of students' work to showcase if you end up doing this activity with your students. But just keep in mind that whenever students' work is published, we need to have them sign a student work release form. And I do have a release form in the handouts that are going to be at the end of the session.
So Denise points out that she's not on Twitter. I think that's okay if you can send, if you want to share your hanger diagram to the Gmail address. I think you can do that too.
Yes.
Stephanie points out that these types of challenges are good for exit tickets, in a class.
Oh, yeah, that's a great idea. And also, if you don't have the ability to post to Twitter, you could describe the diagram in the question area if you would like to.
True.
So I'm going to
see what's popping up on Twitter.
Head over to Twitter right now and refresh. I'm not seeing anything yet.
Although wine bottles would make for an interesting hanger chart. Are people able to share? So there's a question from Catherine about being able to get the issue of the Math Practitioner.
Mm-hmm. I will be sharing that. I see that something came in.
Some people say that they're still working. Oh, there you go. There you go.
No? Yep. How can I turn that the other way?
We can all turn our heads. That's the easiest rotate.
So this is from Mary Dugas. I don't know if I'm saying that right. I hope I didn't just butcher your name. But thank you very much for sharing that with us.
The email address, if you want to send it there, is mathpractitioner@gmail.com.
And we have another one from Danielle.
All right.
Can everybody see that? I wonder if I could make it bigger.
Yeah.
Probably can. There we go. Thank you, Danielle. That's awesome.
William described, I think Williams is similar. He has 6x plus 1 plus 1 plus 1 plus 1 equals 3x plus 1 plus 1 plus 1 plus 1. Gerald wants to know if hanger models would work with systems of equations.
With systems of equations? That's a really good question. How about you try working with that and send me a picture? Oh, now I don't seem to be able to get back to the, oh, I know what I'm doing now, I think. Oops, I think I got another. Share one more picture, and then I think it's probably time to close up shop.
Okay.
So this one comes in from Marsha Bloomberg. Thank you so much. Oh, my email's just dinging, 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 dinging.
Yeah, there you go.
You guys are awesome. All right,
Eric points out that if you want to share your introductory slide, that's a system of equations, no?
the introductory slide. Okay. Oh, I like this because they're not all the same. Everybody can see here what
Yeah.
Nadia sent. This is
Yes.
great. Okay, my introductory slide. This one?
Is that what you mean, Eric? Here, Eric, why don't I unmute you? Where'd you go?
Yes, let's talk about
Hi,
that.
Eric, I'm unmuting you. You're unmuted. You want to speak up? Nope. He's saying not a hanger diagram, but similar.
Right,
Maybe
and
his
I'm glad
microphone's
though
not
that
on.
he mentioned this because this is another great visual model that we didn't have time to really look at today. But it appears in the Tools of Algebra resource that I'm going to share with you. So thank you everyone so much for sharing those, and please continue to share them, send them to me, post them to Twitter. Quickly, I know we're getting close to the time we're supposed to end. This is another resource I wanted to just let you know is available. This is a screenshot from a Desmos activity that I did with my students. I know we're all looking for online tools right now as our students are learning from a distance. And if you're not familiar with Desmos, the activities are designed so students are often asked to explain their thinking, and then their responses are visible to other students. And I really like that feature, especially now when our students are not able to meet together face to face. It kind of helps them to maintain that sense of community. So if you'd like to try out this particular activity at Desmos, it's a hanger diagram activity. There's going to be a handout in the resources for this webinar that explains how to access this activity. And if you have any questions about how to use Desmos, feel free to reach out to me. Wasn't an article in the one of the past issues of the Math Practitioner that I could share with you that goes step by step how to use Desmos, which actually that's how I learned how to use it with my students. So these are the class resources that you can use with your students. If you click on this link after you get the slideshow, it's going to bring you to Collected New York, which has a variety of resources for number of the day. There's also a handout that you'll get at the end of the session that has number of the day activities. And there is so much you can do with number of the day, not just what we did here today. You can just take to so many levels. Something we didn't do today called Always, Sometimes, and Never. It was a really great activity. I've included that as a handout. The Tools of Algebra. I can't say enough good about this resource. And it's actually one in a series of resources that are available at Collected New York. The one-step equations is the Desmos activity. And then there's just a plain handout with the hanger diagram, the first hanger diagram that we looked at. There's also teacher resources. Now, if you're interested in looking at the studies and the research that's been done on why understanding the equal sign really matters and how much of an impact it has on our students' ability to problem solve, these are really great articles to look at. And there's that student work release form. So you can, everything's in that folder if you follow the bit.ly URL there, or if you are able to use the QR code to access the folder. But we'll make that available to you after the webinar as well.
If everything's at that bit.ly, I can just send a PDF of the slides, and then they can use that bit.ly to go and get the documents.
That's awesome. Thank you.
Stephanie was wondering if you could use these sort of hanger schematics to think about balancing chemical equations. I
Oh,
would
I like
certainly
that
think so.
idea.
Yeah.
I love that idea. So Stephanie, if you figure out how to do that, please let me know. Send me uh, send me an email because I'm always looking for really good ideas to put in the newsletter for the math practitioner, and I really like that idea. So that would be a great connection. That would be a great connection.
I used to have a Japanese card game where you had to make molecules. Like you would draw something, and you would have to grab, the various elements in various proportions to make the molecule. So it was a card game where you would win if you got the completed molecule, and that made it very visual in that sense that you were literally building the molecule in front of you. All right. So yes, we are at the top of the hour. I'd like to thank Patricia, I think, for a very informative session. I hope everybody had a okay time communicating via me as the medium instead of being able to communicate directly with her. And hopefully you'll be able to come to some future webinars, and hopefully we can schedule another numeracy related webinar in the future, if not in the next couple of weeks, but going forward, because I've been the program chair of the Angel Conference, co-chair for a few years. And for those of you that come to the conference every year, you know that I really want to make sure that we have a full numeracy strand, because I think it's an important part of the work that New Jersey Association for Lifelong Learning does. So if you have ideas for a webinar, if you have other ideas for how Angel can help spread numeracy resources and share numeracy resources, certainly let me know. And if this will be archived and up on our YouTube channel, and then within the next 2 or 3 days I should be able to send out the certificates and the follow-up information. Okay. All right. Any last minute questions? Everybody's saying thank you, and it was very helpful, and that they learned a lot.
Thank you for coming. I would like to encourage you, if you try out this equation that we started with your students, filling in the box, and try it out. See how your students do, and send me the results. I'd love to compile some data. I'd also like to encourage you to check out the Adult Numeracy Network. The cost of membership is only $20 a year. And the price of membership includes our newsletter that's published 3 times a year, and access to members only teaching resources and research articles. And you get in touch with an awesome group of people that help support you, and can't say enough good about it.
We'll repeat it when I send out the email. I know what's on the slides, but I'll also make sure that we have a direct link to the ANN as well.
Yeah, so thank you everybody so much for spending time, your afternoon on this. Well, it's a beautiful day here.
Yeah, it is here too, yeah.
So thank you for spending a beautiful afternoon thinking about math.
It's always a good day to think about math.
Yes.